Hello and welcome to the last set of videos for our matrices course, Math 220. We're almost done. I have 3 more sections to cover, finish up chapter 4 here. I know we talked a little bit about chapter 4. We kind of did a rushed version at the beginning of chapter 6, and that's because I wanted to use some of this information in chapter 6 to talk about eigenspaces. But I want to come back and just kind of re-describe things, revisit, review a little bit. In fact, this will be a pretty short video, but I want to talk about subspaces. And to revisit that, I'll just write the definition down quickly for you here. What I have here, a subset S of Rn is a subspace if S satisfies the following. Now we remember that S, the set, has to include the zero vector and has to be closed under vector addition and scalar multiplication. Right, now, if we remember what these two things are here, vector addition is that if we have 2 vectors in our set, u and v, if we add those together, u plus v, we should still be in our set. That's what it means to be closed under vector addition. And of course, scalar multiplication is if I have a vector in my set, say u, and some scalar r, that's just a real number. If I have r times u, that should remain in my set. And that's what it means to be a subspace. Okay? So what we'll be looking for is if the set we're working with satisfies those 3 conditions, we can say that it's a subspace for the space that we're in. Okay? I want to look at an example here. Let S be the set of all solutions to the following linear system. x1 plus 3x2 equals 1 and x1 minus 2x2 equals 5. Okay, so the way my set is defined here is it's the set of all solutions to this system. So I solve the system, right? We set up a matrix. We can say here that our set S is equal to the set of x1s and x2s such that the matrix 1, 3, 1 minus 2 times x1, x2 equals that right-hand side 1, 5. Right? That is how our set is defined in this example. It's the solutions to that problem. So we set up our augmented matrix, 1, 3, 1 minus 2, augmented with 1, 5, and we reduce. Right? We reduce, plug this into a calculator. I see that I get 1, 0, 0, 1. And 17/5 minus 4/5. Okay, so that guy is the unique solution to my system. Really, that's the only vector that makes up my set. Here, then S, I'll change my colors. S is the set 17/5 minus 4/5. That's it. That's the only vector in my set. That's the only solution to the system. Is S a subspace for R2, right? I'm in R2. The solutions to the system should be in 2 space. Is S a subspace of R2? Well, is it closed under vector addition and scalar multiplication? I don't think so, but even better, does 17/5 negative 4/5 include the 0 vector? No, not at all. 0 vector 0, 0 is definitely not the same as my solution vector. 0, 0 is not in S, so S, is not a subspace. Not a subspace for R2. That's just it. We look to violate one of those 3 criteria to be a subspace, or just the situation we're in. Does it violate one of those criteria? I'll change the example just a little bit just to show you what happens in a slightly different situation and also to incorporate a new idea or two here. So I changed my problem just a bit. Now let S be the set of all solutions to the following system. The set S is really defined in a very similar way, but my system now is x1 plus 3x2 equals 0 and x1 minus 2x2 equals 0. So this is a homogeneous system, whereas the previous had a specific B vector on that right-hand side. But I set this up very much the same way. I go through and I say my set is obtained from solving the system AX equals 0, and I do that with this augmented matrix, right? 1, 3, 1 minus 2, augmented with the 0 vector. That's my right-hand side. And we quickly see when we reduce this that we get a unique solution that's just the 0 vector. Okay, this reduces to that following matrix, and we have a 0 vector as our solution. Is this set then, the solution, a subspace of R2? Okay, well, let's write that S is the set of just the 0 vector. That's our set. Is this a subspace? So we have to go through our 3 criteria. Does this set include the 0 vector? Well, yeah, it's only the 0 vector. 0 is included in S. Am I closed under vector addition? If I have 2 vectors in my set, 2 vectors that satisfy the equation AX equals 0. So if I write A times U plus V, if I add those 2 vectors together, they should still satisfy AX equals 0. So I'm going to expand this. That's the same as A times U plus A times V. They both satisfy my equation, so those are both 0, which is of course 0, and that is my set. That's in my set. So under vector addition there, I have a vector that's in my set. All that's left to do is scalar multiplication. If I have R as a scalar and U in my set, then A times RU should satisfy my equation. That should be R times AU, and I know AU equals 0. That satisfies my equation, AX equals 0. So I can say that this is R times 0, which is of course the 0 vector. Okay? My set includes a 0 vector and is closed under vector addition and scalar multiplication. I can say that S is a subspace. S is a subspace for R2. Okay? This was a relatively trivial example because our only vector was the 0 vector. If I add the 0 vector to itself, I get a vector in my set. I get the 0 vector. If I multiply 0 vector by a scalar, I get the 0 vector. Right? But just as a quick example, and also to incorporate another type of idea here, what we have, this type of system that we're working with, this homogeneous system, in fact, the set of solutions to the system has a specific name. It's called the null space. In the previous example, S was the set of solutions to AX equals 0. S is said to be the null space of A. The null space of A. And that's a very frequently talked about term. That set of solutions is very frequently talked about. We've been talking about it kind of all semester. We just didn't necessarily use this terminology, but the set of solutions to that homogeneous problem is referred to the null space. Now we know we often talk about these types of things in context of transformations too. We write that null space set as the following. So the set such that A times X equals 0. In context of a transformation, null space, in the context of linear transformations is called the kernel. Now, of course, 2 different names for the same thing. Well, they're mostly the same thing. We very frequently talk about matrix multiplication and linear transformations in the same kind of light. If our transformation is defined T of X equals AX, then yes, of course, these are the same thing when I set that AX equal to 0. All right? But not all the time am I dealing with necessarily a linear transformation or a transformation defined as a matrix. So we do want to be able to talk about these in slightly different contexts. But what this is called is the kernel when T of X equals 0. The null space refers to the matrix multiplication. The kernel of T refers to the transformation. So the kernel refers to linear transformation, whereas the null space refers to the matrix multiplication. Right, so slightly different terminology there, and I want you to be aware because you will see those 2 words used. If you're talking about kernels, you're working with linear transformations. If you're talking about null spaces, you're working with matrices and vice versa. Okay. Coming full circle just a bit, we have back to our unifying theorem here. If we have a set of vectors in Rn and a matrix that's defined by those vectors, and then a transformation that's defined by that matrix of those vectors. this is kind of how everything is tied together in our course here. And we've added 2 more bullets to that. Now, we've missed a few because this is technically before we talk about determinants or eigenvalues and eigenvectors. But those numbers 7 and 8 are new. The null space of A and the kernel of T, if those are both the 0 vector, then all of the following situations are true. Okay. Next, we are going to talk about basis and dimension. Hopefully another quick video. Thanks for watching.